Hello class 11. Today we are going to discuss the second part of motion of a body down an inclined plane. And this second part deals with the angle of inclination theta of the inclined plane with respect to the horizontal, of course, being lesser than the angle of repose. Mind you, theta c is the angle of repose. Okay? So in this case, of course, what happens is, when we have the body placed on the inclined plane, the body is not going to slide on its own. Although there is this component mg sine theta of the weight of the body acting on this body, of course, but still the body is not going to slide down because the angle of inclination is lesser than the angle of repose. And at the angle of repose, what happens? At the angle of repose, the body is on the verge of sliding down. So, mg sine theta, so to say, is still acting on the body, but still, why isn't the body sliding down? The body is not sliding down because there is a force of static friction acting on the body, mind you. So, there is this force of friction. I am not denoting it by any letter right now, but do understand there is a force of static friction acting on it. And the value of the static friction is lesser than the value for its limiting friction, mind you. Okay, so we want therefore the body to slide down the inclined plane for this case when theta is lesser than theta c. Since the body is not going to slide down due to its own weight, so the only other option is to apply an external force, such that due to the application of the external force, what happens is the body starts sliding down. So let us consider a force F acting along the horizontal as shown in the picture. And this force F is acting an angle alpha with respect to mg sine theta, or we can also say it is acting at an angle alpha with respect to the inclined plane itself. So this force F can also be now resolved into two mutually perpendicular components, of course. So this component here is F sine alpha, and since we have two forces acting in the same direction, so therefore the total sum of the forces acting along the inclined plane in the downward direction, of course, is F cos alpha plus mg sine theta. Mg sine theta was already active. Likewise, this perpendicular component of F is F sine alpha. Now in the very same direction again, we already had our normal reaction acting. So therefore the total force acting in the upward direction along the direction of the normal reaction, so to say, is F sine alpha plus R. Okay, now again let us consider, though this force F is acting, say for example the body is on the verge of movement, although this force F is acting, the body is not yet sliding down. Let us therefore consider that scenario, which of course is the scenario of equilibrium. Now, in this scenario of equilibrium, when the body is on the verge of sliding down, what happens is the total force acting on this body has to be zero. The forces should be balancing each other out. So, when the body is on the verge of sliding down, the force of friction that will be acting now, of course, is static friction, but the maximum value of static friction, which is your limiting friction, F of S. Okay, so for the case of equilibrium, that is when the body is on the verge of sliding down, remember. Okay, although so many forces are acting on it. Okay, so what we can write is F cos alpha plus mg sine theta. This force in the downward direction along the inclined plane, it is balanced by the force of limiting friction. Okay, let us say this is our equation 1. Likewise, what we have is F sine alpha plus the normal reaction is equal to mg cos theta, as you can see in the picture. Okay, now we know that f of s is equal to mu s into r, where mu s is the coefficient of static friction, because mind you, the body is on the verge of movement, therefore still static friction we consider. So can I erase this upward part? Okay, quickly pause the video and then copy everything. So I believe you've done that. So let me erase this thing. Let me erase the heading also. Let this be our equation 3. Now see, from equations 2 and 3, from here we can write r is mg cos theta minus f sin alpha. Okay, from equation 2, r is equal to what? Mg cos theta minus f sin alpha, and thereby f of s, substituting this value of r in equation 2, we get f of s is equal to mu s into mg cos theta minus f sin alpha. So this is what we get. Now what we will do is, let this be our equation 4. Therefore, from equations 1 and 4, what are we about to do now? We are simply going to substitute the value of f of s from equation 4 in equation 1. Okay, so let us see what we get then after. Therefore, what we get is, we get f cos alpha plus mg sin theta is equal to mu s into this thing, that is mg cos theta minus f sin alpha. So this is what we get. Okay, and let us try to further simplify it. Let me erase the whole thing over here. I hope you copied this, of course, after pausing the video. Or let us further simplify this. F cos alpha plus mu s into f sin alpha. I'm taking this thing mu s into f sin alpha to the left hand side. So this gives me mu s mg cos theta minus this thing. We are taking it to the right hand side. So this is mg sin theta. So taking f common on the left hand side, we get f is equal to, okay, let me just write, so cos alpha plus mu s sin alpha is equal to mu s mg cos theta minus mg sin theta. If you wish to, you of course can take mg common on the right hand side as well. So from here we get f is mu s into mg cos theta minus mg sin theta, not alpha, sorry, theta, divided by cos alpha plus mu s sin alpha. So let me erase this part now. My board is not very big. Okay, so now the coefficient of static friction can also be written as the tangent of the angular friction theta. Okay, now just to differentiate the angle of friction from this angle of inclination, let me write theta s for angle of friction, where theta s is the angle of friction. I remember I denoted angle of friction simply by a theta, okay, but just to differentiate our angle of friction from this angle of inclination, let us rewrite it as theta s. So theta s is our angle of friction, which is the angle that the resultant of the limiting friction and the normal reaction makes with the normal reaction. Alright, so in case you've forgotten, please go and check that video. Okay, so what we will now do is, instead of mu s in our equation 5, we will rather write tan of theta s. Okay, so let me erase this first. I hope you all are following the mathematics and copying it. Okay, so f is, instead of mu s, you write tangent of the angle of friction into mg cos theta minus mg sine theta divided by the whole thing divided by cos alpha plus, again, instead of mu s, we write tan theta s. Okay, class 11 into sine alpha. So let me erase this part also. So therefore we get f is, let me take out mg common here, mg. So instead of tan theta s, we will write sine theta s upon cos theta s into cos theta in the numerator minus sine theta, since mg is already taken out common, the whole thing divided by, the whole thing is divided by cos alpha plus, again, instead of tan theta s, we will write sine theta s divided by cos theta s into sine alpha. Okay, so let me erase this part. In fact, let me erase the whole thing that's on the lower part of the board. So it's just mathematics that we need to do in here. Or f is equal to, see, what we will do is we'll take out cos theta s LCM. Okay, so this cos theta s in the denominator here, and here also we will take cos theta as LCM, and this cos theta and this cos theta, they divide each other out, because of which we get f is mg sine theta s cos theta minus sine theta. After taking the LCM in the second term, we get sine theta cos theta s cos theta s. Okay, I hope you all are understanding the mathematics. Likewise, we take out LCM cos theta s here. So cos theta s comes and multiplies this term here. So we get cos alpha cos theta s plus sine alpha sine theta s. Let me write it this way. Now, I don't know whether you've learned this in mathematics or not when you are doing a trigonometry, and if you haven't, you will very soon learn about this in trigonometry. That is sine of a minus b. Okay, this will give you sine a cos b minus cos a sine b. This is the formula. Okay, so this is in that form. So a is a theta s, angle a is a theta s, and b is your theta. So this is sine a cos b minus cos a sine b. Okay, so the numerator gives us, so instead of the whole long thing, what we write is mg into sine theta s minus theta. This is what we write, divided by, likewise, cos of a minus b is, let me change my chalk. So cos a minus b is cos a cos b minus sine a sine b. This is the formula. Okay, you learn this in mathematics. Very soon you will learn, if you haven't already. So this gives us in the denominator cos of alpha minus theta s. So cos a minus b is cos a cos b plus sine a sine. Oh, sorry, here is a plus sign, not minus. So after this elaborate derivation, everyone, what we can conclude is, we can conclude that for force F to be minimum, that is the minimum amount of force F that we apply to this body, which will make the body move, the minimum value of F. Okay, we can get that minimum value of F if, of course, the denominator is maximum. Okay, so can I erase this? Of course I can. Okay, I can hear you all say yes. Class 11. So therefore, what we can conclude is, for force F to be minimum, the minimum amount of force that we need to apply to make the body move, so to say, cos of alpha minus theta s is or has to be maximum. It has to be maximum. Okay, now what is the maximum value of cos of any angle, cos theta, so to say? The maximum value of cos of an angle is 1. Alright, so cos of alpha minus theta s, so to say, this implies cos of alpha minus theta s has to be equal to 1, which further implies, or this further tells us, that alpha minus theta s is equal to 0, because cos theta will have maximum value 1 when the value of theta itself is 0 degrees. Okay, so further, therefore, what can we conclude? We can conclude, therefore, alpha is theta s. So what therefore we say is, the minimum value of force F, okay, which will make the body move, has to be applied at an angle theta s, at the value of the angle of friction for this particular system, so to say. So therefore, for F to be minimum, the force F should be applied. Let me erase this part. At an angle equal to the value of the angle of friction. So if we apply this value, or if we apply the force F at an angle alpha which is equal to the angle of friction itself, then the value of F will be minimum.